It's a great pleasure to introduce Peter Scholze from the University of Bonn. He received his PhD under Michael Rappaport, and he specialized in Shimura varieties and the Langley's program. And in 2011, he received our premier award for young people, the Research Fellowship of the Clay Mathematics Institute. He's going to speak to us today on perfectoid spaces.
Thank you a lot for the introduction, and thanks a lot to the organizers for the invitation to speak here. So I want to talk about the theory of perfectoid spaces. And those are somewhat strange objects, so I want to sort of say what they are supposed to be good for. So the sorry. Yeah. Forgot to put it on. It's on. It's on. Okay. Okay. So the aim of the theory is to compare objects which somehow live over an arithmetic field. So objects living over a field in or geometry over mixed characteristic 0p fields with geometry over somehow a field which has one geometric direction, so in equal characteristic p fields. So an example of such a mixed characteristic field that I'm thinking of would be the P-adic numbers, which are, if you think about it, they can be written somehow as formal sums, sort of Laurent series. So I should say that here P, of course, is a prime. Such Laurent series, but somehow the variable is this constant P. So the ANs are certain numbers from 0 to P minus 1. And some of the eco-characteristic P fields that I'm thinking of would be actual Laurent series over the field with P elements. So those are very similar sums. AN times T to the N. And again, the ANs lie in this set, but which we now consider as a field with P elements. And so these fields are similar in many ways, but they're also different in many ways. So for example, here somehow this is a formal variable, whereas this is a constant. So QP has no non-trivial automorphisms, whereas of course this Laurent series field has lots of non-trivial automorphisms, and there are many things that you can do over such an eco-characteristic local fields that you cannot somehow do over the P-adic numbers. And what some of the claim is that's somehow justified by the theory of perfectoid spaces is that the two series somehow over the two different fields, they become in some sense equivalent after you join lots of p power roots. And maybe to be slightly more precise, one should say the étale series become equivalent. So as one example of this phenomenon, let me recall the following theorem, which is due to Fontaine and Winton-Berger. It was proved, I think, sometime in the 60s, that you can look at the absolute Geiger groups of these two fields, and they describe the theory of finite extensions, finite separable extensions of these fields, but they look quite the same, but are really different. But after you join lots of p-power roots, the difference goes away. So the absolute Galois groups of QP to which you join a sequence of p-power roots of p. So by this I mean you take the union of QP to which you join a p-power root of p, p to the nth root of p. And you choose these roots, of course, compatibly. And of this Laurent series field, they are canonically isomorphic. Okay. And the first thing I want to explain today is how to sort of give a maximal generalization of the strange isomorphism of Galois groups and where it comes from, sort of. So for this, I sort of have to explain for which kind of fields you can expect that you can find a different field with the same absolute Galois group, and that's captured by this definition of a perfectoid field. So it's such a field as QP or ZP, these are topological fields. And I assume that it's complete with respect to a non-archimedean norm on K. Such that the following properties are satisfied. So the first thing is that, which I only have to put for technical reasons, is that the image is dense. So in other words, this non-Archimedean field is not discretely valued. And the residue field is supposed to be of characteristic field, P. And the really important condition is that if you look at the ring of integers of K and you use mod P, then also this ring, which is now of characteristic P really, because of this assumption, you have the Frobenius map, and this is supposed to be surjective. So recall that a ring of characteristic P is called perfect if the Frobenius is an isomorphism, and because somehow here we have a similar condition that at least it's surjective, that somehow explains this name perfectoid. So it's somehow something closely related to the condition of being perfect. And so as examples of such field, let me just sort of take the two that will intervene in the understanding this very simple example. So on the one hand, you could take QP and join all of these p-power roots of P. So then every integer divided by a power of P will be in the image of this value of this norm, and hence this will be dense. But it's not complete anymore, so you simply take the completion. If your field is of characteristic P, such as this Laurent series field, then perfectoid fields always have to be perfect, so we simply pass to the perfection here and join all of these p-power roots of T, and then take the completion. And then this will be a perfectoid field of characteristic P. And the Galois group doesn't change when you make these sort of technical things, because purely inseparable extensions don't change the Galois group, for example. And now there's this very general construction of Fontaine, which I've given the name tilting. Which takes any perfectoid field and produces a second one, which is of characteristic P. So that can be a perfectoid field. And so I didn't say that here. OK is a ring of integers of K. So that's the set of elements of norm at most 1. Gives you a subring of K. And then we want to construct a second field, which I call K flat. And its ring of integers will be given by taking this thing here, and you take the inverse limit over Frobenius, and K flat will be its fraction field. Which, as a set, you can also think of, and this will be important later, as the inverse limit over the piece power map on K. But here you have an addition, which is very hard to describe in terms of the addition on K, because, or not quite so easy to describe in terms of the addition in K, because these transition maps here are not compatible with addition if their field is of characteristic 0. And but what this tells you is that in particular you can sort of map determine this inverse limit to its first coordinate, and this gives you a map from elements in K flat to elements in K. And sort of because it's opposite to this flat map as in music, somehow the opposite map is sharp. And the only example, the example again is that if a K is this field of characteristic 0, then K flat will be this somewhat similar looking field in characteristic P. And how can you understand this identification between K flat and this inverse limit over multiplication by P in this example? So this variable T corresponds to the sequence of P power roots of P in this inverse limit. So in particular, if you apply this sharp map to T, it will be P. So somehow, this sharp map is really the map which replaces this variable T by this constant P. So it's really somehow the thing which somehow does the jobs that we are sort of looking for, of replacing this variable T by this constant P. Here's variable T there. But if you, for example, want to understand what the sharp map does to 1 plus t, as an example for a sum, then this gives you a rather complicated P-adic limit, namely the limit as n goes to infinity of 1 plus 1 over p to the n to the p to the n. So you already see that the whole theory will be very analytic in nature It will not be sort of a theory of algebraic geometry, but really some analytic geometry later on. And now the theorem which generalizes this isomorphism of Galois groups is the following. So the first is that in general, K-flat is again a perfectoid field. And the characteristic is always P. That follows easily from the definition. The second part is that if you have any finite extension of your field K, then this will still be perfectoid. And so this means that to any finite extension of K, you can again apply this functor of sort of taking the tilt, and you get a functor from the finite extensions of K to the finite extensions of K flat, which sends L to L flat. And that's in fact an equivalence of categories. And by Grothendieck's formalization of Galois series is precisely saying that the absolute Galois groups of K and K flat are isomorphic. And so this gives you some rather abstract way of defining sort of this functor passing from extensions here to the other side. But you might wonder whether you can actually make explicit so if you have an explicit extension on the other side, can you write down an explicit extension on the other side that will be the corresponding thing? And so in fact that's possible if you go the other way. So say if M over K flat, which is, let me just sort of give an example illustrating how this passage works. So if M over K flat, let's join all of these guys. This is the finite extension generated by, then let me just write down some random polynomial. Then basically what you would like to do is you just replace T by P, and then this extension characteristic 0 should be this extension. But some of this is not quite canonical, so they're different. But it sort of becomes canonical, so M is also generated by a root of x squared minus this guy where you replace T by a large P power root of itself. So because everything here is perfect, you can do this and this will not change the field. And then this field in characteristic 0 that you're looking for will be generated by a root of this thing where now you replace T by P. And now for any sufficiently large n. That's somehow what happens here. Okay, so now there's it pretty much gives you the arithmetic theory, but now we want to sort of compare geometric objects over the two fields. And here's a sort of, what I claim informally is that if you consider the affine line over your field K flat then this is in some sense the same thing as the inverse limit over the piece power map on the affine line over K, where T is the coordinate on A1. So where some the map is given by sending an element of the affine line, which you may, sort of, for example, think of as some element in this field, sort of mapping it to x sharp, and because your field is perfect, you have P's roots, x1 over P sharp, and so on. So you have these two varieties living over very different fields, and still there should be some of this strange relationship relating these two varieties, sort of presenting one as a pro-cover of the other variety. And sort of, let me just give a second example of this, which will be of importance later, is that if you consider the projective space over K flats, and similarly, you can think of this in some way as the inverse limit over the map phi we'll define momentarily of the projective space over K, where phi on homogeneous coordinates is just a piece power map. And so that should also be some kind of projection map, whatever that means, from the projective space over this equal characteristic field to this projective space in this mixed characteristic field. By, again, projecting to the last coordinate in this inverse limit, and some of this would be given on coordinates by exactly this sharp map. Okay, so note that the explicit description of this sharp map, it involved some P-adic limits. Yes? Well, I only consider sort of the last term in this inverse limit, which would be exactly only this x sharp. Right. But sort of if you want to give this map sort of to the whole inverse limit, you would, of course, extract first piece of roots of unity. Yeah. Recall that some of this sharp map, it involves P-adic limits. So this means that when we want to sort of give some geometric structure to this isomorphism, we leave the world of algebraic geometry and we have to use some kind of non-archimedean analytic geometry. And now there's sort of several different versions of non-Archimedean analytic geometry around. So the first one was Tate's theory of rigid analytic varieties. And it's a rather technical theory because some of the underlying space of a rigid analytic variety is not a really topological space, but a Grothendieck topos. And this makes working with rigid analytic varieties technically rather challenging. And so then Berkovich gave a different approach to analytic geometry using his analytic spaces. So these are actually locally ring topological spaces. But they have the disadvantage that the spaces that you glue them out of are closed subsets and not open subsets as you would really like. And then only shortly after Berkowicz's work, Huber defined his adic spaces. And these are really locally ring topological spaces glued out of open affine subsets. So they are technically somehow the most convenient category. And in fact, there's a fully faithful embedding here. So you can consider Tate's rigid analytic varieties as adic spaces. Whereas the relationship with these Berkowitz spaces is slightly more subtle. So you can find a nice subcategory of the three of them, but okay. And so I want to use these adic spaces by Huber. And so the first thing that I will sort of need is that there's this analytification functor which goes from varieties over K to adic spaces over K. X mapping to what I call Xad. And this is the P-adic, the non-archimedean analog of the functor sending varieties over C to complex analytic spaces. And then one way in which this claim above is true is that if you pass to this analytic world by going to the associated adic space, and now this has an underlying topological space, which I denote by these bars, and this is really the inverse limit of the topological spaces on the other side. Take the affine line over K, takes the associated adic space. And some of the same for projective space. Okay, so what you have here is an isomorphism between the underlying topological spaces of two locally ring topological spaces. And so naturally the question arises whether one can compare the structure sheaves on the two sides. Okay. And it turns out that it's possible to do so, but that's not so clear because on this side you really have characteristic P rings, whereas on this side you have characteristic 0 rings. And it's not so clear how to compare rings of characteristic 0 and rings of characteristic P in any kind of natural way. But so you can do the following. So note that somewhere on the right-hand side we get rings like so these brackets here denote rings of convergent power series. And so after you make this transition from T to the P, some of what you do is you join a P power roots of P, and then you take this direct limit here. And so what kind of special property does this ring have? So it's captured in the following definition. Is a Banach algebra over this ring. such that one technical condition is satisfied. But again, the crucial condition is that if you, it's called R, so here R0 is the set of power-bonded elements, and that's somehow the integral subring of R. So an example would be the completion of this. So you again adjoin lots of p power roots, and then somehow you come into this world of perfectoid things. And then some of the amazing statement is that these perfectoid algebras, which you have over K, and which you also have over K flat, one being a category of characteristic zero rings, the other being a category of characteristic p rings, they're canonically equivalent. So we're sending any ring R to somehow exactly the Fontaine construction. So you take the inverse limit over Frobenius on this integral thing mod p, then this becomes an algebra over this ring of integers in this tilted field, and then you tensor this up. So that's somehow the algebraic part, and now we want to associate spaces to these perfectoid algebras. And let me just say that this is possible. So there exists some kind of adic spaces associated to perfectoid algebras. So, and then if you glue them, you get what I call perfectoid spaces over K. And somehow, the example you should think of is really that you take some of your projective space, for example, and then you take this inverse limit over this map phi, which extracts piece roots of the coordinates on and on. That's a typical example of a perfectoid space. Secondly, these categories are equivalent on K over K and over K flat. And how does this equivalence look like? So we send x to x flat here, and they will have the same underlying topological space. And somehow this structure sheaf OX, this will be a sheaf of perfectoid algebras. And the thing for this tilted space will exactly have some of this tilted structure sheaf. That's somehow how you make this geometric. And I should also say, and this is very important for my applications, that one can, as an algebraic geometry, define an état side associated to such a perfectoid space, and which is somehow, in some sense, a refinement somehow of the topological space underlying X. And those two are still, so the état side for X and X flat are still canonically equivalent. One consequence of this result would be, for example, that if you consider the projective space over K flat and again pass to the analytic world and consider its étale topos, then also this is canonically equivalent to some of this inverse limit of the étale toposes for this projective space over K. So this means that this projection map pi is defined on étale sides. So we give more and more structures to this comparison of geometric objects on those sides. And so in the remaining time, I want to briefly discuss two applications of this theory. One is to P-adic Hodge theory, and the other is to the weight monodromy conjecture. So let me start with P-adic Hodge theory, which will be the more abstract application in a sense. So that's about P-adic cohomology. So the first crucial thing which follows from the theorem is that one gets a generalization of Falting's so-called almost purity theorem. That's a rather technical theorem, but it's somehow the main ingredient in Falting's approach to P-adic Hodge theory, which in some sense is the most powerful approach currently to P-adic Hodge theory. Let me just state some other corollaries which are sort of more down to earth. One is that if you start with any affinite rigid analytic variety over K, then X is a K pi 1 for P torsion coefficients. So somehow one problem in P-adic geometry as compared to geometry over the complex numbers is that the local nature of the space is extremely complicated. So in the complex topology, everything is locally contractible. And that's absolutely not true in this P-adic world. But somehow this theorem tells you that at least, maybe it's not contractible, but the only higher homotopy group is pi 1, and all the higher pi 2, pi 3, and so on in some sense vanish, whatever that really means. But you can make this definition of what it means to be a K pi 1. And so somehow in order to make your space contractible in the P-adic world, you somehow have to allow large covers by large finite étale covers of your space. And so let me give an idea of how this is proved. So the first thing is that you produce a large cover, a pro cover, in fact, which is perfectoid. So find x tilde as some perfectoid space such that x tilde and a map x tilde to x, which is somehow an inverse limit of finite étale maps. So this is possible by adjoining lots of p-power roots. And you take p-power roots of 1 units to make sure that the covers you get are really finite étale. then X tilde flat is such a k pi 1 for p-torsion coefficients. Let me omit that. You can deduce this from the Artin tri-exact sequence, for example. And then, because you have this equivalence of étale topoi, you see that also X tilde is such a k pi 1. And because X tilde over X was such an inverse limit of finite étale covers, follows that the same holds true for X. So somehow that's the general procedure to pass somehow to this perfectoid world. You start with something of finite type that you're really interested in, then you make this huge extension of inverse limit of finite étale covers, like somehow for this projective space where you join lots of p-periods of the coordinates. Then you are in this perfectoid world, and then you can somehow miraculously pass to characteristic P, and can then use some information that's only available in characteristic P. And now that somehow you have this good local control in the sense about somehow the P-adic topology of these spaces, you can prove the following theorem, which somehow in P-adic Hodge theory. So first is that K over QP be a finite extension, and X over K. So somehow in classical Hodge theory, what you would start with is a compact complex manifold, and some of the P-adic analog of this would be a proper smooth rigid analytic variety. Let L be a local system on your space which satisfies the condition that it's in some sense of geometric origin. And so there's these sheaves which are called the ROM. There's some arithmetic condition, but everything that is of geometric origin in some sense will be the ROM. And in this case, there's somehow some kind of Riemann-Hilbert correspondence. Which produces for you a triple E nabla fill, where those two form a modulus integrable connection. And this is a filtration on E satisfying Griffith's transversality. So you already see one interesting difference to the complex case here is that local system really correspond to modulus with integrable connection, but together with already the Riemann-Hilbert, the Hodge filtration in some sense, so satisfies Griffith's transversality. So there's considerably more information in such a local system in the P-adic case as opposed to the complex case. But the theorem says that then, if you consider the étale cohomology of X with coefficients, or base change similar to algebraic closure, with coefficients in L, this is we want to relate this somewhat to the ROM cohomology of this modulus integrable connection, and then somehow you have this Fontaine-style comparison isomorphism, which says that after you tensor these up to this big field of P-adic periods, this is isomorphic to the ROM cohomology of x with coefficients somewhere in this E-nabla fill tensor. It's a k vector space. That would be the round. Ron is Fontaine's field of p-adic periods. So what I didn't say, but what's also new is that these groups here satisfy finiteness. So they are finitely generated CP modules. And already this finiteness statement is new and relies on the theory of perfectoid spaces. Okay, and one other thing is that what you can prove in this very general context is that the Hodge-de-Rham spectral sequence will degenerate. And interestingly, no Kähler assumption is necessary for this in the p-adic case. So. And so somehow, if you want to prove degeneration of the Hodge-de-Rham spectral sequence for algebraic varieties over fields of characteristic 0, then if you want to do the sum of this complex Hodge theory, you always have to worry a little bit that just the complex points will not always be Kähler, but so in the p-adic case, you can really directly use this general Hodge-de-Rham spectral Hodge-de-Rham degeneration. And so the second application will be to the weight monodromy conjecture. So and this is somehow about L-adic homology. Well, L is a prime different from P. So some of the interesting things that the theory of perfectoid spaces gives you information really about the étale topos, which means that you can deduce information both about p-adic and about L-adic homology. That's somewhat interesting because these methods that go somewhere into the theory of perfectoid spaces, they were sort of very much conceived by Faltings in this approach to P-adic Hodge theory, and for a long time were only used in this context of P-adic Hodge theory. And so it was rather surprising that you can somehow also prove interesting results and new interesting results in L-adic homology. So what is this conjecture? So again, let me start with a finite extension of QP. And now let me really, and this is necessary, take x over k, a proper smooth algebraic variety. And let me, for convenience, assume that it's geometrically connected. Okay, so then we can look at its L-adic homology, so we base change x to an algebraic closure, and take coefficients in QL bar. So this receives an action of the absolute Galois group of K. And in there, let me choose a geometric Frobenius. what is known about the structure of V? So on the one hand, there is a weight decomposition. Which says that V composes into a direct sum of sort of weight pieces, j running from 0 to I, of a weight space Vj, where all the eigenvalues of phi on the subspace Vj are what are called real numbers of weight j. And such that the absolute value of alpha is q to the j over 2, where for any complex embedding q bar. So q is the cardinality of the residue field of k. So the residue field is a finite field, and q is its cardinality. So recall that somehow, if I didn't start off over a p-adic field but over a finite field, then the Weil conjectures would precisely say that only the summand corresponding to weight I would occur. But somehow a p-adic field, there can be different weights which occur, and that somehow, in some sense, should be made good for by the monodromy action, which is someone the L-adic inertia subgroup. If you look at its action, it produces for you a nilpotent map on the space V, which in fact maps the weight J subspace into the weight J minus 2 subspace. And the conjecture due to the lean is 70 states that Will 2, somewhere 1980, that the analog for a finite extension of this Laurent series field. And so some of the idea now is to reduce the case of equicharacteristic field somehow by using as an intermediary the theory of perfectoid spaces. So that K is just somehow K to which you join, say, all of the p products of P. Okay, and then we have the following picture. So we have this projective space over K, and then somehow we have X, or maybe a space change to K, sitting inside there. And then we have this very strange projection map from this projective space over K flat. And because it's defined in topological spaces, for example, you can really consider its pre-image. And you can get a map on L-adic étale cohomology from the cohomology of X to the cohomology of its inverse image. And if this inverse image was an algebraic variety, we could use Delen's result to conclude. So Delen's result will tell us something about how the Galois group acts on there, and then you can make some argument that somebody will get the same result for X. However, the problem is somehow that even if X is something extremely nice, its pre-image will be some kind of very strange fractal. So That's because some of this map pi is highly non-algebraic in nature. And so in fact, some of x is just this line inside of P2. Then its inverse image is topologically the inverse limit of more and more complicated varieties, giving somehow by replacing these coordinates by their piece power. That's what this identification of the projective space over this equal-characteristic field K flat says with this inverse limit of the projective spaces in mixed characteristic. So this will really be an extremely complicated object. It will have infinite dimensional cohomology. It will meet a line in infinitely many points. So in this sense, it will be of infinite degree, and so on. But we have the following lemma, which sort of gets us through, is that if we slightly thicken our hypersurface, so this is a small P-adic neighborhood, then there exists an algebraic hypersurface Y in the projective space over this equal characteristic field such that Y is contained in the P-image of the slight thickening of X. So we can find a hypersurface which is arbitrarily close to this fractal. But somehow as he makes this neighborhood smaller and smaller, the hypersurfaces will get more and more complicated of higher and higher degree. And okay, so now if we have this lemma, which is somehow by an explicit approximation procedure, then you can you have the cohomology of X, and if X tilde.
So you should just a few more minutes.
Yeah, it's my last sentence basically. You have the slight thickening of X, which is X tilde, and it's just a small neighborhood around it, so you could think that it's homotopy equivalent to X. If you think in the complex picture, you have some variety and so slightly thicken it in the ambient space, and can contract the space bound down to the base, so the cohomology will stay the same. And then you get a map first to this inverse image, and then further to Y. And now for Y, we really can use. So here we can apply Deline's result. And then this way, we really can conclude that for X, the weight monodromy conjecture is true. Okay, that's the end of my talk.
Thank you for a very interesting talk. We have time for a quick question. Anybody? Let me ask a question then. What's the prospects for a general proof by this?
Let's see.
Okay. Okay. Let's just thank the speaker again.